Okay, we're in section 5.6, and we're going to do number 6 together first. So let's start with that. First of all, we have a theorem that's on page 479. It says if y is some function of t that's continuous. So first of all, if I've got it equals f of t, y is a function, right? So we already know it's a function, but it's going to be continuous. It means we can draw it without lifting our pen on its domain, but we also know that when t is greater than or equal to 0, y is positive, okay? So it's on or above the x-axis, right? And we also have that dy dt, listen up, dy dt equals ky. So the Kentucky equation. So y prime equals ky is how you could rewrite that, right? Y prime equals ky, Kentucky. All right, so we have that. So here k is a constant, and when t equals 0, we're going to just call y evaluated at 0 or f evaluated at 0 to be y sub 0. It's the initial value for your output, right, for y or for your function, which is pretty obvious. Just the x-intercept is all, or the, excuse me, the y-intercept, When t is 0, so t is, time always goes on the x-axis, right? Because time is always an independent variable, and then if we have f of t, okay, and when t equals 0, you know, that's your y-intercept. Okay, so this is y0 right here. We're going to call it y0. We could call it f of 0. So y0 is f evaluated at 0, right? Things like that. But anyway, so long story short, then y would equal y0 e to the kt. So this is the formula. So if you have this, so this, for these word problems, you're going to get relationships. Sometimes you're going to get instantaneous rate of change, right? So you got to look for that. What's a derivative? Measures rate of change. So don't forget your Calc 1 lingo when we're trying to do some of this stuff. So if we have the derivative instantaneous rate of change of y with respect to t is ky, then we're going to know by a theorem here that y equals y0, the initial value, e to the kt. So it turns it into an exponential function, right? So let's rewrite it. Instead of using y, let's use f of t notation. So just doing that, this box becomes f prime at t equals k times f of t, right? So if we have that relationship where y is a continuous function and on or above the x-axis for positive or non-negative t's, t is greater than or equal to 0. If k is positive, then this what this becomes is called the law of natural growth. So the law of natural growth, so if we have f prime equals k f of t, k is positive, law of natural growth, we're going to be guaranteed that f of t is y0 e to the kt. So if you're wondering what the heck, what formulas do I use to try and solve some of this stuff, this is a good hint that we're going to use in number 6, right? So we're going to use law of natural growth here. So we had a team of student advisors that are going to give us the output here. And we can use these formulas for growth. We can also use it for if k is greater than 0. This is exponential growth if k is greater than 0. Exponential growth. Well, what happens if k is less than 0? Anybody know?
You can't do it.
Right. If k is less than 0, it's going to be exponential decay. Okay. So anyway, so
Just throw it out
I'm trying to hold that all. That's why we eat healthy, except for the last 3 days of class and then work out and stuff. We want trying to slow down that exponential decay.
We should do a class workout someday.
We should. Yeah. Like an I feel good cheer.
Yeah, right now, let's go.
Right now. Well, I'm on film, so am I recording this? Yeah, I'm recording it. So let's, sit down. He's going to do the cheer and then go for the breakfast pizza. All right, but anyway, so let's do this. What's number 6 say? It is the population of a particular city doubled from 1900 to 1960. So the population, if I was drawing that, what's it doing? From 1900, let's just call 1900 times 0. So instead of calling it 1900, let's let that be 0, right? That's what your group said. And then, and it doubled. So whatever it was here, it doubled by the year 1960. And then what was the problem? What did it ask us to do? If the rate of natural increase of the population, does that kind of sound like this theorem here?
Yeah.
Rate of natural growth, okay? If the rate at any time is proportional to the population at the time, and the population in 1960 was 60,000. So in 1960, we had 60,000 was the population. So if this is population at time t, and this is time t, and let's just call that, did you want to do that in thousands, or did you want to write that out as 60,000 as the number? You want to do it in thousands?
Sure.
So what would the vertical be here? 60?
Yeah.
We don't know what it was in 1900, didn't tell us, did it?
Nope.
Or did it say double?
It doubled.
So what would it be here?
30.
So the y-intercept is 30, right? In this y0? Up above, when t equals 0, y0 is 30, okay? So what do we have? It says rate of change is doubling it. So we have, let's use our theorem up here, dy dt equals k times y, right? Well, which one do we know?
We know K. Wait, no. Yeah, we know K.
Do you?
30K.
Huh?
Yeah. 30,000, is it not?
Where's the y0? What's y equal?
Oh, y of 0 equals 30,000.
Y0 equals 30, so we know that. Y0 equals 30, so we got that one right. We got f of t equals y equal to the kt, but we need to figure out k, don't we? Wasn't that your job? Did you figure that out? Do you know what that is? What is that?
2.
2, why? Because it doubles?
Yeah.
What number is this?
6.
6, okay.
And then you have to
Speak for yourself.
exponent. In the exponent, don't you take the total?
Wait, is k 2 or what's k? Is k 2?
No, K's more complex than 2.
Yeah, which one, what's 2? Like the rate doubles, the rate of change doubles, right? Wouldn't that be dy dt? Wouldn't that be 2? So this is, it's a doubling rate. And this equals k times y, right? But anyway, so now let's go put it over in this equation. So instead of y, we're going to call it f of t, right? Well, what's f of t? It's y0 e to the kt, right? And you said y0 was 30?
Yep.
Okay. So f of t equals 30,000, right? E to the kt, right? So then what'd you do? We still got to figure out k, don't we? So can we use this formula based on what they gave us? In 1960, which is actually 60, what was the population?
1/60th of what it was in 2010, which would be.
Well, we want to figure out the formula first. So the question is, what's the population estimated to be in 2010?
Yeah.
Right? So we need to figure out k though. So f evaluated after the output after 60 years was what? 60,000? So 60 equals 30 e to the k, which we're looking for, times t. How many years was that? 60. So e to the 60, k times 60 or 60k, right? So basically we're using this formula. So f of t, the output was the 60,000 people, right? 30 is my y0. That was the population at time t equals 0. And then e to the kt, but this is 60 years down the road. So don't let this 60 and that 60 confuse you. One is the number of years in the exponent. The other one is the population in thousands. It's just ironic that they happen to be the same number, okay? But just drawing a picture for me always helps. This always helps me, okay? Anyway, so how can I do this? Well, solve it. So divide both sides by 30, right? And we get 2 So we get 2 equals e to the 60k. So the question is, how do you solve for k?
You set y, y of t, you need to find what? K, or y of k. Well, you have to find the time.
Well, we have the time, but so we're not going to answer the question of what's the population going to be in 2010 yet. We need to find k to do that, right? How do I solve this equation right here for k? Let's do this in, let me erase this. Take the natural log of both sides, right? So the natural log of both sides will undo the e. So basically the natural log of 2 equals 60k. So solving that for k is natural log of 2 divided by 60, which is going to give us, I mean, that's the exact value of k, right? We could get an approximate on that as well, right? Or the other way to do that is plug it in for what we want. So there's a couple different approaches here. I don't want to erase too much because I don't want to forget what I put down, even though it's your group's responsibility, right?
Yep.
So what's my function? F of t equals 30e to the kt, right? So f at time t, so time t, we're going to estimate this for 2010 as 110 years after 1900, right? So we want to find f of t equals what when t equals 2010 as 110 years after 1900, right? So we'll plug it in. Anyway, but what's f of t equal? It equals y0, which was what? 30?
Times 2, would it be, since it is.
Well, it can be. I'm just going to do what everybody else would do that wasn't working on this problem. E to the kt. So it's e to the ln2 over 60 t, right? It's going to be 110. So that's one way to do it. That's an awkward way. What did you call it?
You have to multiply the 30 times 2, and then you put the exponent up there, right? And then it would be t over 60 because it's the total rate of change or yeah.
I think so. Could I do this? Could I rewrite it?
Yes.
Amen rule, right? So this is 30, and then how do I rewrite that? E to the ln2 to the 1/60th power, right?
Mm-hmm.
Could I rewrite it like that? And then that quantity to the t. What's e to the ln2? 2. So this is equivalent to 30 times 2, that's 2, right? To the what? T over 60 power? Okay, so this is what you might see if you were, if it was telling you to come up with the equation in the book, they might have this and you might be like, how in the world did they get that, right? But they're just using rules of exponential functions and log functions to rewrite this stuff. That's all. I think you said something back here. If I have 2 equals e to the 60k, the question, then what would 2 to the 1/60th be? 2 to the 1 over 60 equals e to the k, right? If I take the 60th root of both sides, I think, yeah. So really what I could have done is come back here. When I put e to the k, I could have rewrote that as 2 to the 1/60th and then to the t. That, I think you said that.
Yeah.
Okay, and you were right, but I stepped it through a different way. So we could have rewrote it just f of t equals 30. 2 to the 1/60th was e to the k, and then quantity to the t, which ends up being 30 times 2 to the t over 60 power, right? Anyway, long story short, now we can answer the question finally, right? This is why we're doing this stuff together, because it's not easy unless you do it right. And then so f of 110 equals 30 times 2 to the 110 over 60, or 11/6 power, which is approximately, anybody got a calculator?
I got 106,907.
106,907? You mean we?
908.
Well, are you rounding up?
Yeah, well, it had a point, there was a partial person.
Partial person?
Yes.
Okay, so here's where real life comes in. It was 907 point something.
Yeah.
Okay, well, yeah, you might like actual people. I mean, you're estimating anyway, but you need to go nearest person, so you can't have a tenth of a person, right? Without going to jail. So this is, but what was this output? Was this people or thousands of people? So now you got to pay attention to how you label your variables.
This was when we multiplied it by to get back to the
So you had, so it was 100.
It would be 10 point.
106.908, right? But this is thousands people. Anybody got a calculator out? This is thousands of people, and then you just change that to. So let's say it was 907.8 whatever. But anyway, 106,908 people.
So would you change it?
Well, yeah, this is a better.
You would round, but if you did it that way, would you round to 107,600 since the decimal's there this time?
107,000.
Well, like when it's.
No, because you want it to the nearest person, probably. So you're going to want to keep that decimal, but then make it in like how you would talk in real life. People, right? Does that make sense? Is that the, oh, you don't have the answer in the back of the book, right? But did anybody else get that on your calculator? 106,908 is, that's essentially what the book would get. You know, if you put approximately 107,000, I mean, you could have done that too. So that was the question. Hey, what if I just call that as about 107 because it said approximate, then about 107,000 people? You know, that's okay. It's not quite as good of an estimate, but an estimate is an estimate anyway, and it's not going to be right. So we're just trying to be close. Both of those are close, and most likely I would accept them both, but I would rather, if we're going to estimate, I'd rather not estimate along the way. So the other way you could have estimated, somebody could have put in 2 to the 160th power and got some decimal, right? So if you get that 2 to the 160th power, get some long decimal, and then you just abbreviate that at the hundreds place, plug that in to our formula where we came up with this. This is going to be off too, right? You're just making it off even more and more and more. So try not to round until the bitter end. Bitter end. Remember, we're trying to slow down that decay. Yeah, the exponential decay. We want exponential growth in your learning and future. Yeah, baby. All right, there you go. So that's number 6. I'm going to stop this and do a different one for